Background. I work full-time as a professor at St. Clair College, and I teach sessionally at the University of Windsor, at the School of Business, and the University of Niagara Falls. I obtained my Bachelor of Computer Engineering and MBA from Wright State University in Dayton, Ohio. It is named after the Wright brothers that invented the airplane, so the logo here is basically the two brothers, one of them watching with excitement, and the other one is actually on the airplane. I then went on and got my Master's in Information Security and PhD at Nova Southeastern University, and that is the mascot of or the logo of the university. It's a shark, it's in Florida, there are sharks, I guess, nearby Florida. And I am authoring a book with PAC Publishing, and I suppose most importantly, I am part of the GBG Windsor community. I get to work with Rob every other week, maybe, okay, for cybersecurity stuff. So I'm lucky I get to see him more than you do, for some. I am co-authoring a book. It's called Building Responsible AI with Python. It has been years in the making. It turned out to take a lot longer than I anticipated, but it's going to come out within the next, hopefully, few months, sometime next year. So I'm going to ask the question to all of you, why responsible AI, or what is it? So I need some help here. I need you to tell me what is responsible AI, or why should we care? Go ahead, Rob.
For unbiased data results.
Unbiased results, okay, one. Okay, anybody else? Go ahead.
Things can go really wrong.
Things
Can go wrong.
Things can go wrong, okay, and well, let somebody else play, Rob. Okay, go ahead, Si.
For more transparency?
For transparency, okay. Anybody else? Okay, let's go. Now, we don't really care too much about responsible AI if we're using AI to play a video game, unless you're really using that game to the AI, and that's a potential issue. Or if it's recommending a movie. Okay, yeah, that gave you a movie that you didn't like, so what? Okay, it doesn't really matter. But if we go back and start using AI in making high-stakes decisions, is this person guilty of that crime? Should I perform this procedure on somebody? Should this student get into this high-prestige college or university? Should I approve this loan, or should I hire this person? If we are delegating decision-making on things that matter to AI, well, there are a few questions that we should ask, right? And this is a problem that is getting bigger because a lot of what AI is doing is being concentrated in a few big tech companies. You see some of these confrontational hearings with big tech executives. Tell me about your algorithm, okay? How are you deciding, or how are you doing this, or asking questions, because these big tech companies like Google, our sponsor today, are starting to hold a lot of power over our daily lives. So we need to have some type of agency, some type of control over what are they doing with these algorithms, or anybody who's putting an algorithm that has an impact on our lives. It's important for us to be part of that conversation. So I am going to switch to the idea of fairness. So what is AI fairness, and why do we do this? Can anybody, I gave you some example of use cases. Can somebody tell me what would be a case of a decision that is unfair? Here, let's take a look. With all of these decisions, can you think of an AI algorithm making a decision and how that decision made up? Go ahead.
Hiring someone just because of like the race or gender over someone else.
Yeah, I'm a brilliant woman, and they hired a dumb man instead of me because he happened to be a man. Okay? Okay. Yes, go ahead.
Maybe in the financial institutions where you apply for a mortgage, for example, and then having a different result just because of who you are.
Yeah, I mean, having a different result on your mortgage application, not because of your financial characteristics or history, but because of who you are. You happen to be a woman, you happen to be a person with a particular ethnicity, that's it, okay? Now, it turns out there are many definitions of fairness. In fact, there's a paper that talks about 22 definitions of fairness. So what is fair has some complexity to it, and I'm going to try to expand on that a little bit. In laws, there are laws in the US. A lot of this is based on US laws, but it does fit into Canada. I think the Canadian laws are, in terms of fairness and AI regulations, are catching up, but they're getting there. So there's the Fair Housing Act, Equal Credit Opportunity Act, Equal Employment Opportunity Commission. All of these are laws and regulations in the US trying to figure out or trying to have some definition, some notion of fairness. So I'll start with what is the harm, right? When you are considering a decision that's being made, one of the things you want to think about is what is the harm that is being done out there. And one type of harm we can qualify is the quality of service harm. A quality of service harm means the algorithm does not work well for everyone. For example, this paper out there, it was a New York Times article in which the label of it is facial recognition is accurate if you're a white guy. Okay, and that the error rate for white men is 1%, for white women it's 7%, for men of color it's 1%, and a whopping 35% error rate for women of color. Okay? So this is an example where the AI model does not work well. It's inaccurate for different groups of people. In fact, just for fun, I'm going to pull up this YouTube video, which I have it prepared here. It is a YouTube video of the racist soap dispenser. So this is a, well, and of course you're not seeing it. Hold on, okay? Hold on, let's see it. Okay, here it goes. Okay, we made it. So this is the racist soap dispenser. Okay, and the idea is this. This gentleman with dark skin puts in a hand to get some soap. Nothing. Absolutely nothing. And then puts in a white sheet of paper and look at what comes out. Soap. Here we go. One. I give you the punchline. There it is. So why do you think something like this happened? I mean, obviously this is a quality of service harm. The model would work well for a person with light skin complexion, but does not work as well for somebody with dark skin complexion. Why do you think we have a case of the racist soap dispenser? Go ahead. Yeah, go ahead. You want to say something?
Right, I was going to say because of the training data.
Training data, right? So this could be an example where the training data, or they just forgot to test it on people with different skin colors, right? So no soap for you, okay, is the harm in this particular case. Anybody remembers this? Anybody old enough to remember this? Okay, here we go, yes. So that is one type of harm. The other type of harm is allocation harm. Who gets what? Right? I have a certain number of jobs and I'm going to offer them to 10 people. Who's going to get those 10 jobs? Or who's those 10 college admissions? Or who's going to get allocated that $10 million worth of lending that I need to put out there, right? And we are not grappling with these questions for the first time in the age of AI. In fact, they are questions that were discussed, well-defined, and well-established in Title VII of the Civil Rights Act of 1964. Right? If you go back and read the language of the Civil Rights Act, Title VII, you will find language such that I'm going to explain to you right now. So they talk about individual fairness and group fairness. I'm going to use those references of the Civil Rights Act language of fairness in discussing AI. So we start with, well, this is important. We should probably do an audit on our AI models before we actually put them in the wild to make sure we're not causing any harm out there. And an AI fairness audit should include, at a minimum, an explain task, explaining what the model is doing, measuring what the model is producing in terms of fairness and accuracy and whatnot, mitigation intervention, right? If you were to find something that is unfavorable or something that is objectionable, you want to mitigate and then monitor to make sure that after you put things in production, things did not go wrong, right? That's the general idea. So I'll start with explain. Why would explaining the logic of the model be important? Or in what context would it be important? Why do I need to understand the logic? Go ahead.
Because if you want to diagnose the problem, you have a problem with fairness, then you need to understand it, be able to diagnose it.
Okay, so you need to understand what's driving the unfairness. Okay, somebody else in the back, you want to say something as well, or?
Yeah, like
Go ahead.
when you make a bank loan, you want to make sure the decisions were fair, not like biased.
Okay, so you want to make the basis in which the decision is being made, you want to make sure that there's some fairness to them. And what we're talking about when we're examining the logic of the model is the idea of individual fairness. And by individual fairness, we mean similar people are treated similar treatment. And that, there's a couple of ideas here. Similar means I am using characteristics that are acceptable in that context. So if in the context of a bank loan, I am only using your credit history, your outstanding loans, attributes about you that are not objectionable. I should not be using protected class attributes, in which there are laws against discrimination for these protected class attributes. I should not be using the fact that you're a woman. You say, well, you're a woman, deny loan, things of that sort. So one way or one reason why we want to understand the logic of these models and explain why are these models coming up with their predictions or decisions is we want to understand if they are using objectionable characteristics or protected class attributes in the decision, right? The other aspect of individual fairness that's really important to think about is even if the model was individually fair, you could end up with group unfairness. Which means, even if I use the same qualification, the same criteria, I could end up with some level of group disparity where I use the same decision, but I ended up only approving 90% of men, but 10% of women, right? At that point, you want to go back and just say, okay, my model does not explicitly say deny women, and I'm using the same non-objectionable criteria, but I am actually ended up somehow discriminating against women without having a specific rule to do so. So when you're doing an audit, obviously we start with the obvious, explain the logic of the model, and we've looked at what that means. If it's a woman, they'll hire for an IT role, that would be an objectionable. So why would explaining and I would argue, explaining the logic of a model is very difficult. And I would like to know why if you agree with me, tell me why. If you disagree with me, also tell me why. The statement that I'm making is, explaining the logic of a model is difficult. And whether you agree or disagree, I'd like to know why. Yeah, go ahead.
I think one of the key aspects of it's so difficult is that you're trying to make it understand it on a specific perspective that you need to, but to get to that perspective, you also need to get it like on a broad and concrete knowledge. So it gets to that specific point of view, and I don't know, it doesn't get to the bias or not bias. So it's still hard to not having a detour.
Okay, so context, complexity of the environment in which the model operates in, okay, that's fine. But I guess maybe if I can focus the question more specifically, I have a model. I'm giving this model 100 variables. And I'm just saying, give me a prediction, is this person going to repay the loan and should I approve or not? And even without looking at the social context which you talked about, I would argue that that's still a difficult thing to do. Now go ahead, now that I reframed the question.
Perhaps it's because focused on the outcome, and we treat the model like a black box where
Okay.
we're not really understanding why it's deciding the things.
Yeah. So the point here, and I think it's one that I agree with, is we basically train a machine learning model by giving it a whole bunch of data and giving it accuracy metrics that we wanted to achieve or wanted to do as best as it can on that accuracy metric, and just say, figure out a way to give me accurate predictions. And if I leave that model alone, it's going to figure out some way of getting to that objective, and I don't really have I don't really have an understanding of how it got there, because the model is a black box. It's a black box because of complexity, right? I could give you this structure of a neural network and just say, this is your model. And your explanation is all of these things happening between all of these weights, all of these measures, all of these connections, all these neurons. Here's why I decided on approving that mode. This is complex. Human cognition does not scale to a level of that complexity, right? Now, if somebody were to say, but what about decision trees? Right? We've heard of decision trees where if I'm trying to understand if this animal is a penguin, I start with the question of, does it have feather? False. Does it have fins? Okay, well, does it have feathers? True, but can it fly? False. It must be a penguin. That's a decision tree. That's an explainable model. It's too factual, but no, but I am looking for a factual explanation from a model. A model is a mathematical calculation that's going to give me a prediction of this person has a 70% probability of repaying their loan. And I'm just giving it a whole bunch of variables and getting a prediction. I could end up with a decision tree model that does this, okay? You were gonna say something, go ahead.
Right. What's your baseline?
What do you mean your baseline?
What is your baseline? Where are you making your decision on your
Well,
baseline?
in supervised learning, I am measuring the performance of my model against label data. So I give it a whole bunch of examples of loans that I've approved in the past, and then I just say, learn to do whatever I did in the past, or learn to approve loans that have been repaid in the past, and give me accurate predictions about the future.
Your data change your hypothesis.
Your data could change your hypothesis. There's a lot of things that could go wrong, yes? But the question in this particular section is, I built a decision tree. Why can't I just use that as my explanation? Because the structure of the decision tree is my explanation, right? And let me just, because there's a lot more ground to cover. Well, if your decision tree grows beyond a certain scale, you're back to the same problem that you had with neural networks, right? So if your decision tree is all of this, and that's your explanation, well, then I'm back to the same problem that I started with neural networks, right? So even a tree-based model, like a random forest or an XGBoost or something along those lines, can end up being a black box model, even though you can look at the structure, because I did not put a cap on complexity, right? So it's a complexity problem. Now, there are solutions to these complexity problems. One solution out there is to examine local explanations. So rather than try to focus on the explanation of the logic of the entire model, maybe try to come up with an explanation of that single record, right? And you can end up with different explanations based on the individual record. So why is this person going to have heart disease? Because they have high cholesterol, they're overweight, and high blood pressure. But this person is not likely to have the same level of prediction because they have different conditions. So by narrowing or zooming in on a local explanation versus the global explanation, in some cases, those approximations can actually simplify your explanation. So I will just put out there, I can't go through it in the amount of time I have, but there's something called SHAP or Shapley values. I would urge you to look into what it does. And what it does, it does a lot of work, it basically is a post hoc explanation trying to explain the logic of the model after the fact by approximating the interrogating model. Okay, so let's go back. What I said earlier is I could have decisions that are individually fair, but we can end up with group unfair to a group. right? And when measuring group fairness, it is important to think about it in the context, okay, I have a privileged versus protected group, or a reference versus unprivileged group. So in society, if I were to ask men versus women, who's privileged and who's unprivileged? Right, who's historically disadvantaged in their workplace? It would be women, okay? Black versus white, okay, or something along those lines, right? So you have, there are historical references for discrimination enshrined into law where you have protected class attributes in which we can use to say, how is this group doing relative to their peer from the other? So how are women doing versus men? A person from this race versus a person from that race. Okay? So this is where we're looking at the favorable outcome of a group, and we're looking for disparate impact or statistical parity. Is there a significant difference between these two groups in a way that would cause us to just go take a look back and just say, are we doing something we shouldn't? Right? And so I'll ask you this question, pop quiz. 95% of men are approved, but only 5% of women are approved. Is this a group fairness problem? Yes? Yes. Okay, yes, well done. Okay, what about this? 95% of men are approved, but 92% of women are approved. Is this a group fairness problem? No?
It is.
No, it is not. There are natural variations, right? There's randomness in any type of decision making, randomness in any data, and if the difference is small enough, it's random, right? Versus if the difference is significant, then you would go and just say, wait a minute, let's take a pause and examine what we're doing. Here, yes, they're different, but there is some randomness. It could have gone the other way around. Okay? So I'm glad that I checked here. Okay. So probably not. It's not statistically significant. Now, one of the ways there are mechanisms for. There are many metrics. I can spend 4 hours just talking about metrics for fairness, but we're going to do one today just to give you a flavor of fairness metrics. So one metric that is commonly used is something called the adverse impact ratio, and where you put in the percentage of favorable decisions on the numerator and the percentage of favorable decisions for the other group, so protected versus reference, in the denominator. Now, let me ask you this. If both groups were of equal, basically have the same favorability rating, 70%, what would the AIR be? 1. Okay, perfect. What if the protected group had a very low percentage, 20% versus 90%? Would it be 0.2 over 0.9? Okay, is it over 1 or less than 1? Less, okay. What about 0.8 over 0.2? Over 1, right? So you have a simple measure, the favorable outcome, and keep in mind, we are measuring the favorable outcome, not the accuracy of the model in this case. Right? I could give a favorable outcome and be wrong. Right? So this is not a measure of accuracy, it's a measure of group fairness by saying what is the favorable outcome for this group versus that group if I use this model. Or another measure of fairness when I talk about quality of service harm, is the model being really accurate for one group but not as accurate for another group. That's another measure of favorability. So the thing to keep in mind is you want to measure model usage, not model predictions. And what that means is this. Let's say I have a credit prediction model. I'll just say I have some applicant data, all sorts of things. I put that into a prediction model, and anybody above a certain threshold, so below a certain threshold of risk score, I basically get them either a high risk loan or a low price loan. So if you have high risk, I'm going to give you a high risk loan, a high price loan versus a low risk loan. And when I do something like this is one of the examples we actually talked about in our book, where we spread out the percentage of approval. Okay, let's say I approved 5%. And then I approved 10%, or I approved 100%. At 100% approval rate, our AIR is going to be what? 1. Everybody got a loan, right? So at 100% approval rate, both groups got a favorable rate, right? Now, if I start saying I'm going to approve 95% of my applicants, then I start to see a small number for the AIR. So you could come back and just say, maybe my model is making some prediction disparities, but if I set my threshold high enough, I managed to reduce the disparities between the two groups that I'm trying to equalize to some degree in terms of fairness to a certain level. So you're not necessarily just looking at the predictions of the model, but what is the final decision made based on using the model in this context, and are there things that I can do after the model prediction to come up with some level of minimized disparity. Got it? Okay. So we've talked about measure. Now, okay, fine. I built a model. My model sucks. What do I do now? I built a model and it's horrible. What do I do? How do I mitigate? Huh? What?
Like do a new model.
Train some more?
No, just do a new model, just joking.
Okay, okay. Well, it's, okay, go ahead.
Feed more accurate data.
Well, no, the data is accurate. I gave it accurate data. But, well, first of all, real life is not fair. Okay? In real life, we do some pretty nasty things to people, okay? So, it's not a data accuracy problem, no.
And I guess maybe human intervention.
Okay, how?
You do it in a more manual process, basically.
Okay, so you can basically, well, then you defeated the whole purpose of automation, right?
Yeah.
If I'm gonna have to look at every decision, but the thing is, you can't look at every single decision because these decisions could be individually fair, but unfair to a group, right? So I'm going to talk to you quickly about some mitigation techniques. So one idea out there is fairness through unawareness. The other idea is fairness through affirmative action. And then the third idea is fairness is an optimization problem. And let me just go through the first one. Fairness through unawareness. Here we go. Lady Justice. It's a blind person holding the scale, and the scale is even, right? That's the idea of fairness through unawareness. I'm colorblind. I don't have the attributes of the person. If I don't know that you're a woman or you're a person of this particular ethnicity, how can I discriminate against you? What do you think of that idea?
Might work.
Okay, and it might not. Why may it not work?
Maybe the bias shows through some of the other data.
Okay, yes, 100%. So this is the problem with proxy features. If you tell me which neighborhood you live in, I kind of have an idea of what your racial background is. If you tell me you have a lot of experience, I know you're really, really old. Okay? If you tell me you shop for pink dresses a lot, well, you're probably a woman, or you're a very romantic person that buys a lot of dresses for their wife, okay? But either way, okay, you should not get a lot. Okay. Okay, let's not go there. Okay. But, so fairness through unawareness is generally problematic because the model, you may want to do it anyway, but it has limitations because the model will figure out other mechanisms of coming up with the same decision, right? So not necessarily something. Then fairness through affirmative action, you basically say, well, if you're a person of this particular group, we don't have enough of you, so let's take the first top 2 people from that particular group, right? And this is contentious in the US recently, the Trump administration, they're fighting it and whatnot. So it has a lot of history and basis in South African apartheid regime, where this was actually implemented over there as a way of making up for historical injustices against people of particular group membership. But today, I would say it is controversial and some people are fighting. Okay? So we want to come up with something different. And I would argue that fairness as an optimization problem is the approach that I think we should all attempt to do. And what does that mean? So I start with the idea of fairness, the multiplicity of good models. And that means this. If I try to predict ice cream sales, I can predict ice cream sales based on temperature, right? Or based on the time of the year, the month. Either one could be used as a predictor of the label that I'm trying to do, correct? So the point that I'm trying to say, the multiplicity of good models, is there are, when you're building a machine learning predictive model, there are many versions of these models, many possible options of logic that you can choose from to come up with that prediction. There's not one single answer. Make sense? So conceptually, that's what it is. So the idea here, it's a design choice. I could have 100 models, all of them have some level of accuracy. I can choose which model to implement based on not only accuracy, but accuracy and a fairness constraint. Right? And what I'm looking for is, I want a model that's highly fair and highly accurate, and there I have a whole bunch of models to choose from. I could just put it on a matrix, and I can generate with enough training examples, multiple versions of the model. So in your training, when you're doing your model selection, just look for a model that is fair and accurate. Whatever your fairness metric is, whatever your accuracy metric is, add it as a constraint during training. Now, in some cases, accuracy, individual, and group fairness are conflicting objectives. Right? So you understand that you're putting in competing objectives for this mathematical optimization problem of minimizing error, maximizing group fairness, doing this, doing that, don't use these features. And eventually, the goal is to have a model that meets all of these conditions. Now, if you did your best and you ended up with some model that has objectionable attributes, then there are debiasing techniques that you can put in that can help you build a model that's accurate and also needs some level of fairness. Okay. So we've talked about, okay, so here's, and I am showing you here 3 broad classes of techniques that we would use in this context. So pre-processing, in-processing, and post-processing. And by that I mean, okay, so let me ask you this. Anybody here who's a machine learning developer took a machine learning class? Yes? No? Okay. So when you have an imbalanced class, right? A minority class and a majority class, what do you do there?
Oversample.
You oversample, you undersample. Go ahead. So you go ahead. You want to say something?
I think you take the minority class and you synthesize data,
Okay.
the numbers.
So you take the minority class, make more dummy records of it, so you make it overrepresented than it really is in the data, and you oversample, or you undersample the majority class, right? Those are techniques. Or you can do things where you do cost-sensitive learning. So the general approaches are, you oversample the minority class, or you undersample the majority class, or you do something called cost-sensitive learning, where you're getting the model to pay a higher penalty for being wrong than the minority class, right? And that idea is not too different. Just if you add a fairness objective to it, manipulate the training data to give maybe oversample the favorable decisions for a minority class or something like that sort, right? Now, in processing, well, there's another, I would say, I was going to say this was in processing, but I come to think of it, it is pre-processing, okay? You can do something called a majority-only model. So build the logic of the model based on the majority class, and then apply the majority-only rule for everybody. Right? Because if your hypothesis is the majority class is being treated better, okay, so go learn the rules of being treated better and ignore how we're actually doing for the minority class and apply that. Now, you can do this and it may not work, and a lot of the times it doesn't, but this is one option of things that you can try. And then there is this idea of adversarial debiasing. And this falls under the category of in-processing. So the idea is this. I have a predictive model that's optimized for accuracy, and I have another model that's an adversary that's fighting with this model. And the adversary's job is, if you told me the prediction, I'm going to be able to predict the race of the person. If you told me whether or not you approved the loan, or you did this, or whatever, or you got that college admission, or the favorable decision for hiring was made, I'm going to be able to predict the race, gender, or what have you of that person. And the idea here, we're challenging the predictive model, go in, try to find an accurate model prediction system that does not allow me to know the race of the person at the end of your predictions, right? And this is an iterative process, right? It's a process that goes back and forth until you get to a point where the predictive model figured out a way to come up with a prediction without knowing whether or not the person is of particular race, ethnicity, etc. Okay, so that's adversarial. Now, the last point here is, yeah, go ahead.
Just a quick question. As a person of color, when I play from the data,